Okay, so to get started on this 6-7, what we're going to look at is just some of the applications of integration that you would study in physics and mechanics and so forth. So first of all, I want to look a little bit at this formula, mass is equal to density times volume. Typically, the units go like this. This is worth writing down. When you study physics, units are kind of what helps you understand formulas. So like mass, typically you would have in grams, okay? And let's see, the next one is like density is typically in grams per cubic centimeter, okay? And then volume typically would be like cubic whatever, so cubic centimeters like that. So see, and whenever you look at physics formulas, the units work out. So if you had grams, if you have mass being grams, and then the density is represented by rho, okay, that's the Greek letter rho, R-H-O, okay, and that goes like this. Its units are grams per centimeters cubed, and then you multiply by the volume. So notice what happens is those cross out. See, the units work that way, okay, so that's how your units go for density, is it's gram per cubic centimeters or grams per cubic whatever, meters or whatever, okay? So typically what we have is we're going to look at a density of an object when it varies. So if you're studying physics, this formula right here, just the general formula, would be like if you had an object and the density was constant throughout that, okay? And there's a lot of things that are like that, that are made where it has constant density to it, but most things have variable density to it, okay? Right? I remember this when I was in college. There was a fraternity called Rho, Rho, Rho. I thought that was kind of clever, okay? When I was a rock star back in the day, I used to play in a band called Pyro. And our symbol was pi for pi and rho for rho. That's what we had on the drummer. We had like something like that. We thought we were so cool, pyro. Okay, so I always think of that when I think of rho. Okay, so the idea with this is you have some. We're going to just kind of look at a rectangular bar. We kind of keep this simple at this stage right here and kind of look at how the calculus goes. So what we're looking at is some sort of a rectangular bar, and that again is what we limit this to, but the density is variable. So at any point it may have more density, just meaning the molecules are packed tighter, and in other places they're looser, so it doesn't have the same density throughout. So what we do in calculus is we kind of break this thing up into little pieces like this, and we do integrals on this. So what we're looking at is we're kind of slicing this up into just real tiny pieces like this, okay? And then that's going to be like your delta x is just like an infinitely skinny rectangle like that, okay? And then the idea is going to be we're going to sum these things up. So you kind of got to sum k equals 1, and all that means is that's like your first rectangle, and then that n would be like your nth rectangle like that, and then you're doing rho, which could be represented as a function typically, okay? If you have variable density, one of the things you try to do is represent that density with some sort of a function. Then you have delta x like that. So the idea is like we've been doing, it's the same idea is when we do the limit of the Riemann sum, what we end up doing is, so if we do the limit as n goes to 0 of this Riemann sum, which is what it is, well, then what we do is we get an integral, okay? Because we're taking that in going to infinity. What that means is we're just using infinite numbers of rectangles. So we're dividing up into tiny slices. So then what you would get is this would end up being the integral, and that would be like from a to b, okay? And then we would have rho of x times dx like this, okay? So that right there is your density right there, and then this right here is your volume, okay, like that. So that's what you end up getting for your basic formula like that. Okay, does that kind of make sense? And that's what you do with integrals, is you break things up into little tiny pieces and then resum them together. So that gives you the general formula that we're going to use in calculus for finding a density. So that's what the density is equal to. Okay, so that just kind of gives you an idea of why that's an integral, hopefully. Does that make sense to everybody? Okay. All right, so on the next page, this is what we have. Okay, so we're going to look at basically in this particular case right here. So we have, again, we were using the formula mass equals density times volume. So let me get to where I need to go here. Okay, so you might make a note on this. That's the mass. Okay, and then this is the density. That's the rho. And then the dx becomes the volume. And the volume typically is, the typical unit would be cubic centimeters. And then for density, the typical unit would be grams per cubic centimeter. And then mass is like grams like that. So you want to know how your units go like that. Okay? So actually, the problems that we start off with are pretty simple. It's just trying to get the idea of how you can use this as an integral. Okay? So what's happening down here on this first example is you have like just some sort of a 2 meter long bar, and all that would mean is you just got some kind of a mass like this, and it's not uniform density. It's not like the same density everywhere. Some places the molecules are packed tighter than other places. Does that make sense? It's variable, and that's when you use calculus. So the idea on this is you kind of got dx is just going to be like the volume. Now see, this is a three-dimensional thing here. So you're looking at a bar that has, 3 dimensions to it like that. So that's your dx like this. And then this time rho, the density is given as a function. Okay, so that just means that if you evaluated x, that would give you the specific density in grams per, and this one is in kilograms per meter in this particular problem. Okay, so what you do on this is you're going to find, you've got the interval 0 to 2, so we're kind of looking at from 0 to 2, and let's see, we've got this, so we're going to find the mass of the bar. So the mass is going to just be equal to the integral. We're going to be integrating from 0 to 2. You can kind of put that bar on the x-axis, and then that would be rho of x dx like that. So that means that would just be the integral from 0 to 2 of 1 plus x squared times dx like that. Okay, and that's a super easy integral to do. Okay, so that means when we do the antiderivative of this is going to be x plus x to the third over 3, and then we're going to evaluate that from 0 to 2. Okay, so if we do that, we're going to have 2 plus 2 to the third over 3, and then minus 0 plus 0 to the third over 3. So that looks like that's going to be 2 plus 8 thirds minus 0. You can put that over 1 and get a common denominator if you want to. So let's see, that's going to multiply by 3 over 3. So that would give 6 thirds plus 8 thirds. So that would be 14 thirds. Okay, now mass, what did we say the units for mass were? Okay, grams. Now in this case it's kilograms because that's what the problem says. So the key thing is kilograms is what you have there. So we're going to go ahead and say that that's 14 thirds kilograms like that. So that's real simple. We don't really do a whole lot with finding mass other than just introduce the idea that it's an integral. Okay, so it becomes mostly a practice in working integrals, but it's sprinkling in an idea that you'll see in physics, okay, if you're going to take that. Okay, now the next problem's kind of the same way. Okay, you're going to find the mass on this one. This time I didn't really give you any units. So the mass on this is, again, the integral from a to b of rho of x, which is the density, times dx. So again, that's your density, and that's the volume. Okay, so we're using the formula that we know. Okay, so what we're going to do on this one is integrate from 0 to 4. Okay, that's given the bar. Okay, and then the rho, the function for density, is 5e to the negative 2x, and then times dx like that. Okay, so that's going to be the integral that we work out to get our answer then. Okay, so this is a pretty easy integral. So you just bring out the 5. So you're going to have 5 times the integral 0 to 4 e to the negative 2x dx, like that. And remember this formula that I've got on the board. You see this all the time, so you want to make sure you know that. What is that? That's 1 over k e to the kx plus c. Okay, so when you work with that integral, you want to know that without having to do u substitution. So that'll be 5 times negative 1/2 times e to the negative 2x, and then evaluate that from 0 to 4 like that. Okay, so let's see if we work this out. You can put that over 1. That would be negative 5/2 like that, and then we're doing the integral e to the negative 2x from 0 to 4. So that's going to be negative 5/2 e to the negative 2 times 4 minus e to the negative 2 times 0 when you evaluate the integral. And it looks like that's going to be negative 5/2 times e to the negative 8. And then that's e to the 0, so that becomes 1. So what we would have from here is, I'm just going to write this like this. There's several ways you could write the answer. I'm going to write, we know that's 1, and then e to the negative 8, you can leave it alone or you can make it a positive exponent. And then that would just be whatever the units are, like grams or kilograms or whatever like that. Okay, and then that would end up giving you the density on that then. Okay. And if you wanted to, sometimes we do this on a calculator also, so I'm going to go ahead and just get a decimal on a calculator also. So I could go like negative 5/2, get that answer. Okay, then I could multiply that by parentheses 1 minus, then I'm going to put 1 over e to the 8th, like that. Okay, just to crunch that out into decimals like that. Okay. So about negative 2.5. Okay, does that make sense, dear buddy? Go ahead.
Doesn't the 1 have to be negative? Yeah. I did be like.
Oh yeah, we're getting a negative answer for mass anyway, so that's kind of, okay. Yeah, right here would be, that would be minus 1, wouldn't it? Yeah, that's minus 1, so that doesn't make, you got to have a positive mass, okay? So the thing on that is if you calculate that with the calculator, we need to change that then, so. So that would be like negative 2.5, and now it'll give you a positive answer. So that would be like negative 1, and then minus 1 over e to the 8th, like that. Okay, so that's better, 2.5, positive 2.5. Okay, whatever the units are then. Okay. All right, any questions about that? Okay, so that shouldn't be too bad. I mean, the integrals aren't too bad on that. That's kind of the basic idea. Now, another thing that you get into a little bit is piecewise functions quite a bit. So a lot of times, and this is very common in physics, you might have a bar, and what this one is kind of representing, again, is we're still talking about different, at some sort of a rectangular bar, and what this is defined to be is from 0 to 2, actually it's just the density is equal to 1 unit, like grams per cubic centimeter or something like that. And then from 2 to 4, you have a different density, which is represented by the linear function, rho is equal to 1 plus x, like that. So if you're going to find the density on this, well, you got to do 2 integrals. So the idea is the mass, you'd have to do 2 different integrals because there's 2 different functions. So the first thing you would do is you'd do the integral from 0 to 2 of rho, which is 1 times dx, so you'd have to work that integral out, and that would take care of that piece right there. Okay, then the second piece, you would have to set up a different integral for that, so that would be plus the integral from 2 to 4, and then that would be rho, which is 1 plus x times dx, like that. So if you have a piecewise function, those are given the density, so you basically got to sum those two things up like that. So when we do this, then the integral of 1 would just be x, and then we'd evaluate from 0 to 2. The second integral of 1 would be x. Integral of x would be x squared over 2, like that. And we'd evaluate that from 2 to 4 like that to get that final solution then. So this would be, first integral would be 2 minus 0, excuse me. And then the second one would be 4 plus 4 squared over 2. And then minus 2 plus 2 squared over 2, like that. Okay, then just work out the details of the arithmetic. So you'd have 2. That would be kind of like the mass for the first part. Okay, that would be mass is equal to 2, like this. And then when you get to this part, it looks like you would have 4 plus, and then this is 16 over 2, so that's 8. And then this would be minus 2, and then this would be 4 over 2, so that would be 2. So this second part looks like you would have, bring this down, you would have 2 plus, and then that looks like 12 minus 4, so that would be 8. So then this part right here is going to have a mass that's equal to 8. So it looks like the total mass on that would be 10 whatever. So it could be grams or whatever. I didn't really give you the units on that, so if not, you just say 10 units, okay, like that. Okay, how's that look? That should be easy compared to what I've done today. I mean, that's just pretty straightforward integrals. And that's essentially what we do with that, is just introduce the idea to you, okay? Now we go with the idea of work. We're going to learn something called Hooke's law. That's a pretty good thing to look at this level. So first of all, what I wanted to do, let's see, kind of on the bottom here, is just kind of introduce you to the formula. Then on the next page, we'll kind of look at the integral and talk a little bit about Hooke's law. So I do want to introduce you to Hooke's law today too. So basically what work is defined to be is it's like a force on an object over a distance, okay? And there's a couple of things that probably you might want to write down on here, because you'll deal with this, and those of you who are taking physics, when you start dealing with forces, you'll do this. So the units go like this, like a Newton. This is worth writing down. A Newton is a gram, what is that? Gram, I wrote it down somewhere. I'm not a physicist. Yeah, kilogram meter per second squared. I remember this when I was a student. So kilogram meter per second squared is what that is. Okay, that's a Newton. Okay, and then a work is typically in a joule. Okay, and a joule basically is this. It's basically a kilogram meter squared over a second squared, like that. Okay, that's what work is, because all it is it's taking a force times a distance. So the idea with this is, here's how the units work out. So work kind of goes like this. That's a joule. So I'd like to show you how these units work. A joule is a kilogram meter squared per second squared, and that's equal to a force. Whoops, I need to write this like this. A force is like a Newton, named after Isaac Newton, of course, is a kilogram meter per second squared. And then a distance, of course, a distance would be something like a meter or something. Okay, so see how that works? Is you have a meter times a meter is a meter squared. So that's what a joule is. So when you start studying about this, if you're going to do engineering and physics, you work with newtons, and joules is the general thing that you use for work. Okay, so that's the idea. Okay, let's see. The next page I'm going to show you, there's kind of a diagram, then we'll define the calculus, and then we're going to do just a little bit. I probably have time maybe to do one Hooke's law formula like this. So this is basically what work is saying. It's basically you're applying a force to a distance. Okay, so the distance might be A to B like this. And again, what you're doing on this is the reason that we use calculus is because the force may vary. Okay, like if you were pushing an object at a constant force, then you wouldn't have to use calculus. You would just do this formula. You would just do force times distance and get work, but that's only if the force is constant. Now it's variable, and that's why calculus is all over the place in physics, okay? So the idea is we're going to basically do this idea of we just kind of increment the forces, and then we look at the distances. So the distances become dx in this case. So we just chop that distance up, and then the force becomes a function. So what we end up saying is the work is basically the integral of the force, and that will be a function that will be given to you. At this stage it has to be. And then the dx is just going to be whatever that distance is like that. So it's basically just doing force times distance is equal to work like that, okay? So what I want to introduce you to is the idea of Hooke's law, and then we should have time to do one basic thing here. So basically if you have a spring, Hooke's law basically says the force required to keep the spring compressed or stretched is given by this formula. So it takes force, a certain force to compress and a certain force to stretch, okay? And it's linear on that. So that is a linear function on that, where K is just some sort of a constant. So when you study about springs, they have some sort of a constant on that. Some springs are very hard to stretch, some are very easy. And it depends on what that value of K is. And it's linear. So that's what K is that just kind of is a measurement of how stiff the spring is. Okay, that's Hooke's law, Kx. Okay. Now I'm going to work one example out that's pretty straightforward. This is kind of what you'll get into a little bit in Hooke's law. So first of all, this is what you're given. It says that it takes a force of 10 newtons. Whenever you see N, that's newtons. Okay, then you're stretching that a distance of 1 meter from equilibrium position. Okay, what does equilibrium position mean? It just means the spring is just sitting there. It's not stretched or it's not compressed, right? So if you stretch a spring, what's going to happen to it? It's going to go ding, 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 ding like this and eventually come to rest, right? It's going to wobble. Okay, you can actually model it by a sine wave that goes and it damps. It comes to an end like that. So it'll kind of wildly wobble for a while, then it'll come back to equilibrium. So that's the idea. So first of all, Hooke's law is this formula. F of x is equal to k times x. Okay, so the first thing is in this problem, you're given enough information to find k. They didn't give you k, but they gave you all you need to know. So basically, the force is going to be 10 newtons. Okay, k is what we're trying to find. The distance is going to be 0.1 meters like that. So then you can go through and you can solve this for k. So you can divide both sides by 0.1 meters like that. And then k, you can go through and do 10 divided by 0.1, which is 100. And k is a constant. Okay, it doesn't have any type of a term in it. And you can just pay attention to this, but if you had a newton over a meter, which is what you have, a newton over a meter, what that really is it's a kilogram meter per second squared, okay? And then those meters are going to cross out like that, okay? So that K is just going to be some sort of a constant force like that. That's what you have. So what you're going to do now is you're going to find that spring constant, and then we're going to solve some problems on that. So if you're given a force required to stretch a spring a certain distance, then you can always find K like that, okay? So that would be kind of the idea, is that would be 100. Now, the question on this becomes how much work is it going to take to compress the spring 0.5 meters from its equilibrium position? So the general formula for work is we're integrating from A to B of the force, f of x, which we now have, times dx like that. Okay? Now the part of this sometimes that students struggle with is these integrals, is the limits of integration. So basically, Hooke's law says f of x equals kx. So we just got k was 100. So what you have is 100x. That's going to be your force function is going to be 100x times dx like that. Okay, so you got to first of all find k if that's not given to you like that. Okay, now what's happening on this, the way I look at this is kind of like this. Now you got to be kind of cautious about how you do this. If you're compressing, then you're going into a negative direction. Okay, if you're stretching, then you want to model that with a positive number. So you want to use a positive on that. So the way you do this, equilibrium is just kind of starting at 0 like this. So you're actually compressing this. And think of it as going in a negative direction. What you kind of have is you have your spring kind of going like that. That's your spring, but you're compressing it in that direction. So you have to use negative 0.5. Okay? And it's okay that the order of the integration is that way. It doesn't matter. Now, if that problem was stretching, then we would use 0.5. So compressing just means we're moving in the negative direction. Okay, like that. So now if we integrate this then, this is an easy integral to do. You would have 100 as your constant. The integral of x is x squared over 2. So that would give 50x to the second. And then we have to integrate that and evaluate that integral from 0 to negative 0.5. Okay, so when we do that, we're going to have 50. We're going to have negative 0.5 squared. That's going to square anyway on this. And then 0 squared like that. So that's 50. Let's see, 0.5 squared is what? 0.25. And then minus 0. So then if you take 50 times 0.25, what is that? That's like 12.5, I think, because it's half of a half. So it would be 12.5. Okay, and work, typically what we say on this is we say joules. Okay, so the final answer on that, we would write that as 12.5 joules. Now, when you do your problems on that, the integrals aren't going to be that big of a deal. It's more the concepts that you're learning. So that would be the idea is compressing, be sure that you use a negative. You're always going to start at 0 if you're starting at equilibrium point like that. Okay, does that make sense? Okay, now let's see. I want to finish here with just these last couple of problems here. Let's see. This one says how much work is required to stretch the spring. Okay, so if you do this, now you would go, how would you do the integral? 0 to where? 0.25. You have to use a positive because you're stretching. Okay, then it would be the same thing. It would just be 100x dx like that. So you're stretching. So this would end up being 100x to the second over 2 with your antiderivative from 0 to 0.25. So that would be 50x squared from 0 to 0.25 like that. So that would be 50 and then 0.25 squared minus 0 squared. Then you can just use your calculator on that. So that's 50 times, and what is that? 0.625. Yeah, so that would be, what is that? Yeah, okay, I'm trying to do it. Yeah, 625, 0.0625 minus 0. Okay, and if you do that on your calculator, you can check me on this. I think this is 3.125 joules is what you should have there as an answer. Okay, so that's what you're going to do if you end up stretching that then. Okay. All right, and this one let's finish up just by setting up the last one. This one says how much additional work is required to stretch the spring 0.25 if it's already been stretched 0.1, like this. So basically what you're doing with this one, when you do the work on this, now you're still integrating the 100x times dx like this. But what this one is saying is it's already, instead of starting at equilibrium, it's starting there. So what this would be, that upper limit would be 0.1 plus the 0.25, like that, okay? So if you did that, that would be 0.35, like that. So you're going from 0.1 to 0.35 times dx like that. Because this time you're not starting at equilibrium, you're starting at 0.1. Does that make sense? Then you're just adding the 0.25 to that. So that would be 100x squared, evaluated from 0.1 to 0.35. So that's 100, over 2, like that. So the antiderivative of that would be 50x squared, like we've been doing, and then evaluate that from 0.1 to 0.35. So that's going to be 50 times 0.35 squared minus 0.1 squared. You can do that all on the calculator. So what I'm getting on this is 5.625 joules if you work that out, because you can get your calculator on that. Okay, so that's the idea. Okay, so does that make some sense? Okay, you got to find k first unless it's given to you, and the key is setting up those limits. Yes.
Work will always be a positive number, right?
Mm-hmm.
It can't be negative work.
Yes. Now you can have, you can represent your distances stretched and compressed by plus or minus, depending on the direction.
So, like, this is kind of a stretch for question, but like, if you had a system that was having work done on it, could it be expressed as negative work?
I think since it's, let's see, since it's a force, now forces can be represented by negative and positive numbers, and a distance is going to be positive.
So you could have, like,
I think so. I'm having trouble figuring out a instant what that is because I'm not a physics expert,
yeah,
unfortunately.
So like work being done on.
But that's something that would be, I think, a